Part 1. The opaque wall at the edge of everything. There is a wall at the edge of the visible universe. Not a wall in the way you might imagine one. Not rock or metal or any material you could name. It has no surface you could press your hand against. It carries no texture, no color in any wavelength your naked eye could detect. But it is real, in every physical sense of the word real, and it is the hardest boundary in all of cosmology. Beyond it, our telescopes go dark. Our radio dishes fall silent. Every instrument ever built to observe the cosmos, every satellite we have launched into orbit, every lens ever ground, every dish ever pointed skyward, all of them hit this wall and stop. The wall is made of light. More precisely, it is made of the oldest light in existence. A faint, cold, extraordinarily ancient glow that fills the entire sky in every direction simultaneously, so uniform and so evenly spread that for decades after its discovery, scientists could barely believe it was real. This light was released approximately 380,000 years after the Big Bang, at a moment so specific and so physically decisive that physicists have given it a formal name, the surface of last scattering. Behind it, stretching back in time to the very first instant of the universe's existence, lies everything we cannot see. Everything we cannot detect directly. Everything that happened before the universe became transparent to light. And there is an enormous amount of everything back there. Think about what that number actually means. 380,000 years. It sounds substantial. It is, on a human timescale, an almost incomprehensible span of time. Anatomically modern humans have only existed for roughly 300,000 years, so the era we cannot see predates our entire species by a comfortable margin. But in cosmic terms, 380,000 years is nothing. The universe is approximately 13.8 billion years old. That means the wall separating us from the unseeable early universe falls at a point when the cosmos was just 0.003% of its current age. We are looking at a universe that had barely begun, a universe that had not yet made its first star, its first galaxy, or a single atom of the elements that would eventually build everything you have ever seen or touched. And even that almost newborn universe is hidden from us, because everything that happened before it is locked away behind this ancient wall of fossilized light. To understand why the wall exists, you need to understand what the early universe actually was. Not what it looked like from the outside, which is what telescopes show us. What it was on the inside, in every direction, at every point in space, simultaneously. The early universe was a plasma. Not the kind of plasma in a neon sign or a welding torch, though those are the same class of physical state. The early universe was a plasma so hot, so dense, and so energetically extreme that the concept of solid matter was simply not available as an option. There were no atoms, not even close. The conditions that allow an electron to settle into an orbit around a nucleus and form a stable atom require temperatures low enough that photons, particles of light, cannot simply blast the electron back out again with their energy. In the early universe, photons had so much energy that any electron attempting to bind itself to a proton was immediately and violently ionized back into freedom, over and over, endlessly, for hundreds of thousands of years. This means the entire early universe, in every direction, was filled with a hot soup of free electrons and protons and photons, all of them colliding with each other so rapidly and so frequently that the universe was, in every practical sense, opaque. A photon released at any point in that plasma could not travel any significant distance before colliding with a free electron and being scattered off in a new direction, then another, then another. The universe was not dark in those early days. It was blindingly, overwhelmingly bright, but that light was trapped, pinballing endlessly through a fog of charged particles that refused to let it travel freely. This is the key to understanding the wall. Light is our primary tool for observing the universe. Virtually everything we know about distant galaxies, distant stars, distant structures, all of it comes to us in the form of electromagnetic radiation of one wavelength or another. Radio waves, infrared light, visible light, ultraviolet light, X-rays, gamma rays. They are all versions of the same thing, electromagnetic radiation, just at different energies. And all of that radiation requires a transparent medium to travel through. The early universe, for its first 380,000 years, was not transparent. It was a fog so thick that no photon could escape it. Then, at a moment that physicists calculate to extraordinary precision, the universe crossed a temperature threshold. The temperature dropped to roughly 3,000 Kelvin. Hot, but cool enough that electrons could finally bind to protons without being immediately blasted apart again. In a transition that took several tens of thousands of years, the universe transformed from a plasma of free charged particles into a gas of neutral hydrogen and helium atoms. Neutral atoms do not scatter photons nearly as effectively as free electrons. The universe, almost overnight in cosmic terms, became transparent. And in that moment, every photon that had been trapped in the plasma was suddenly free to travel. Released simultaneously, from every point in the now transparent universe, they streamed outward in every direction. They have been traveling ever since, for the next 13.8 billion years, while stars formed and died, while galaxies organized themselves into vast networks, while the universe expanded and cooled, those ancient photons kept moving. And tonight, right now as you read or listen to this, some of them are arriving at Earth. They are arriving from every direction equally, from a sphere surrounding us at a distance of about 46 billion light-years. And when our instruments capture them, they have been so stretched by the expansion of the universe, redshifted from visible orange light all the way down to cold microwaves, that they register at a temperature of just 2.725 Kelvin, barely above absolute zero. This is the cosmic microwave background radiation, and it is the wall. We call it a wall because it is literally the last surface from which information in the form of photons can reach us. Look in any direction, and you are looking at this surface. It is around us on all sides, equally distant in every direction, the spherical boundary of our observable universe. Beyond it, in the direction of earlier times, photons cannot carry information to us because the medium through which they would have had to travel was opaque. It is as if you were standing in a room full of extremely thick fog. You can see the fog itself, the surface of the fog, where visibility drops to zero, but you cannot see what lies beyond it. The surface of last scattering is exactly that fog bank, except the fog is made of primordial plasma and the room is the entire universe. What makes this wall strange in a way that goes beyond mere observational limitation is what it implies about our knowledge. We are not just talking about a technical challenge, build a better telescope, resolve a finer detail, detect a fainter signal. We are talking about a fundamental physical barrier. The information about the first 380,000 years of the universe does not exist in photon form accessible to us. It was either absorbed, scattered, and lost in the plasma, or it was encoded in forms of radiation that interact with matter too weakly for our current technology to detect. The first 380,000 years of existence, the era that included the Big Bang itself, the formation of the first protons and neutrons, the cooking of the first atomic nuclei, and whatever physics drove the universe into existence in the first place, is hidden behind a curtain that light itself cannot pierce for us. And yet the wall is not simply a dead end. It is, if you know how to read it, a document. The surface of last scattering carries the imprint of everything that happened before it. Every density variation, every subtle temperature fluctuation, every acoustic wave that propagated through the primordial plasma, all of it left marks on the surface of the wall, the way a fingerprint leaves marks on glass. The cosmic microwave background is not just a barrier. It is a fossil record of the early universe, and physicists have spent decades learning to read it. But reading the fossil record of the CMB only gets you so far. It tells you about conditions at 380,000 years. It cannot take you back to 1 second, or 1 millisecond, or 1 microsecond. For that, you need a different kind of messenger, something that travels through plasma without being scattered, something that passed through the opaque fog of the early universe as if it were not there. We will get to those messengers. But first, let us spend some time with the wall itself, because understanding what you are looking at when you look at the CMB is one of the most quietly astonishing experiences modern science can offer. Before we continue, wherever you are watching this from, drop it in the comments. The city, the country, the time. It is genuinely something, knowing that people all over this planet are sitting with these same questions in very different corners of the world. And if you are not subscribed yet, now is a good time. We are just getting started. Part 2. What the wall is made of. Reading the oldest map. When the Planck satellite, a European Space Agency spacecraft launched in 2009, completed its survey of the cosmic microwave background and the results were processed and released, what emerged was a map, not a map of geography and not a map of any star or galaxy you might recognize. A map of temperature fluctuations across the entire sky. A full-sphere image of the oldest light in existence. The image looks, at first glance, like a multicolored egg. Warm colors, reds and oranges, mark regions that are slightly warmer than average. Cool colors, blues and greens, mark regions slightly cooler. The variations in temperature across the entire sky amount to differences of about 1 part in 100,000. If the average temperature of the CMB is 2.725 Kelvin, then the hottest spots are 2.7250273 Kelvin, and the coldest are 2.7249727 Kelvin. The map of the entire sky's temperature variance fits within a range smaller than 3/10,000ths of a degree. This extreme smoothness is itself one of the most important facts in cosmology. The early universe, at the moment the CMB was released, was almost perfectly uniform. Matter was distributed almost identically in every direction. Temperature was almost identical everywhere. The universe was, at 380,000 years old, a place of extraordinary homogeneity, a fact that requires its own explanation, and which we will come back to when we discuss inflation. But the almost in all of those sentences matters enormously, because those tiny temperature fluctuations, 1 part in 100,000, are not random noise. They are structured. They have a specific pattern, a specific statistical distribution, a specific relationship between fluctuations of different sizes. And that structure is the fingerprint of what was happening in the plasma before the photons were released. In the period before recombination, the universe was filled with a fluid, a mix of photons, electrons, and protons, that behaved according to the physics of fluids. Gravity was pulling matter together in slightly denser regions. The photon pressure was pushing back against that gravitational compression, like pressure building up in a compressed spring. The result was acoustic oscillations, sound waves, propagating through the primordial plasma. Not sound as you experience it in air, but the same basic physics. Pressure variations propagating through a medium at a specific speed. These acoustic oscillations had been running for 380,000 years by the time the CMB was released. At the moment of last scattering, the oscillations were frozen in place. Dense regions had slightly higher temperatures. Rarefied regions had slightly lower temperatures. The snapshot of those frozen oscillations is what creates the pattern we see in the CMB. The characteristic sizes of those temperature fluctuations correspond to the wavelengths of sound that had time to complete specific fractions of an oscillation in 380,000 years, the universe's sound horizon, the maximum distance that acoustic information could have traveled before the plasma turned transparent. This frozen snapshot is extraordinarily information-rich. The specific pattern of fluctuations, the relative heights of different frequency peaks in what physicists call the power spectrum, tells cosmologists with remarkable precision about the composition of the universe at the time of recombination, how much ordinary matter was present, how much dark matter, the geometry of space, whether it is flat, positively curved like a sphere, or negatively curved like a saddle, even the age of the universe. From the most recent Planck data, the universe consists of approximately 5% ordinary baryonic matter, the protons and neutrons that make up atoms. About 27% is dark matter, something that exerts gravity but does not interact with light in any way we can directly detect. And approximately 68% is dark energy, a form of energy associated with space itself, driving the accelerated expansion of the universe. What dark matter actually is, what dark energy actually is, These remain among the most pressing open questions in all of physics. But the CMB tells us they must exist, with a precision that leaves very little room for doubt. The acoustic oscillations frozen in the CMB also left their mark on the large-scale distribution of galaxies we observe today. The same sound horizon that determined the pattern of temperature fluctuations in the CMB established a preferred length scale, roughly 500 million light-years, for the clustering of matter. Galaxy surveys have found this baryon acoustic oscillation scale repeatedly, in datasets spanning billions of light-years. It is the universe remembering, in the structure of its galaxies, the music it was playing when it was less than 400,000 years old. All of this astonishing precision, all of this information about the composition and geometry and history of the universe, all of it comes from a single snapshot taken at 380,000 years, from just one moment in a 13.8 billion year history. And what happened in the first 380,000 years, the era that the CMB wall hides, contains everything that determined the initial conditions of that snapshot. The composition of the universe, the nature of dark matter, the seeds of structure, the asymmetry between matter and antimatter that allowed anything to exist at all. All of these were established in the era before the wall. This is why physicists are not content to simply read the wall. They want to see past it, and to do that, they need tools other than light. Part 3. The first 3 minutes. Fire and the first matter. Let us go back, not to 380,000 years, where the CMB wall stands, much further back than that, back to when the universe was 3 minutes old. 3 minutes is a strange unit of time to apply to a cosmological event, but the first few minutes of the universe's existence were so physically decisive, so packed with irreversible once-in-cosmic history reactions, that they deserve to be treated as an era unto themselves. George Gamow and his collaborators in the 1940s worked out the broad outlines of what happened in this era, and the theory they developed, Big Bang nucleosynthesis, has since been confirmed by observation with a precision that ranks among the great triumphs of scientific prediction. At 3 minutes old, the universe had cooled to approximately 1 billion Kelvin, 1 billion degrees. The temperature at the core of our Sun is about 15 million Kelvin, so the 3-minute-old universe was roughly 65 times hotter than the center of a star. Under those conditions, the simple nuclear physics of proton and neutron interactions becomes the most important process in the cosmos. In the first second of the universe's existence, the temperature was even more extreme, around 10 billion Kelvin. At that temperature, protons and neutrons were being constantly converted into each other through weak nuclear force interactions. A proton would absorb an electron antineutrino and become a neutron. A neutron would decay into a proton, an electron, and a neutrino. These interconversions were happening so rapidly that the ratio of protons to neutrons was determined purely by the temperature and the mass difference between the two particles, protons being slightly lighter than neutrons, so protons were marginally favored at equilibrium. As the universe expanded and cooled toward the 1-second mark, the rate of these interconversion reactions dropped below the rate of universal expansion. The neutrons and protons effectively decoupled from each other, and the ratio froze at approximately 7 protons for every 1 neutron. Free neutrons are unstable. They decay with a half-life of about 10 minutes. So the universe was in a race. It needed to incorporate those neutrons into atomic nuclei before they decayed away into individual protons. The first step was combining 1 proton and 1 neutron into a nucleus of deuterium, heavy hydrogen. Deuterium is fragile. At the temperatures present in the very early universe, photons had enough energy to blast deuterium nuclei apart as fast as they formed. This deuterium bottleneck is why nucleosynthesis could not begin immediately. The universe had to cool enough for deuterium to survive before the heavier elements could form. Around 3 to 4 minutes after the Big Bang, the temperature dropped to roughly 1 billion Kelvin, the threshold at which deuterium could survive the photon bombardment. And at that moment, a burst of nuclear reactions ran through the entire universe simultaneously. Deuterium nuclei fused together to make helium-3. Helium-3 absorbed another neutron to make helium-4. The process was efficient and fast, and by the time the universe was about 20 minutes old, and the temperature had dropped too low for further significant fusion reactions, the basic chemistry of the universe was fixed. The outcome was approximately 75% hydrogen by mass and approximately 25% helium-4, with trace quantities of deuterium, helium-3, and a small amount of lithium-7, no heavier elements. The conditions that allow stellar nucleosynthesis, the slow cooking of carbon, oxygen, silicon, and iron in stellar interiors, require the sustained gravitational pressure of a star. In the 3-minute window of Big Bang nucleosynthesis, the universe could only manage the lightest elements. When we observe the oldest, most chemically primitive objects in the universe, ancient, metal-poor stars in the outer halo of the Milky Way, or pristine gas clouds at extreme distances illuminated by the light of distant quasars, we find the same elemental abundances predicted by Big Bang nucleosynthesis. Roughly 75% hydrogen, roughly 25% helium, trace deuterium, and a small amount of lithium. The agreement between theory and observation is extraordinary. It is one of the primary pillars supporting the Big Bang model. There is one notable exception, the lithium problem. The predicted abundance of lithium-7 from nucleosynthesis calculations is about 3 times higher than what is measured in the oldest stars. This discrepancy has been known for decades. It might be an observational artifact, a result of lithium being depleted by physical processes inside old stars over billions of years. It might point to new physics at the energy scales of nucleosynthesis. It remains an unresolved puzzle, a small but persistent crack in an otherwise remarkably successful prediction. But the nucleosynthesis calculation only works for the first few minutes. Going further back, before the formation of the first atomic nuclei, before even the first protons and neutrons, requires a very different kind of physics, the physics of the quark-gluon plasma. And that is where the universe's history becomes genuinely strange, and the limits of what we can probe experimentally begin to bite hard. Before about 1 microsecond, 1/1,000,000th of a second, after the Big Bang, the temperature of the universe exceeded about 100 billion Kelvin, and the density was so extreme that individual protons and neutrons did not exist. The quarks and gluons that make up protons and neutrons were not confined inside discrete particles. They existed in a free, roaming state, a quark-gluon plasma, in which quarks and gluons moved independently, interacting as a hot liquid rather than as separate bound particles. Researchers at CERN, using the Large Hadron Collider, have recreated small samples of quark-gluon plasma by smashing lead nuclei together at extreme velocities. What they found was startling. The quark-gluon plasma behaves not like a gas, but like a nearly perfect liquid, with the lowest viscosity of any substance ever measured. It flows with almost no resistance, a hot liquid of fundamental particles that existed for the first microsecond of the universe's existence, and has not been a stable state of matter anywhere in the cosmos for approximately 13.8 billion years since. At about 1 microsecond, the universe cooled enough for quarks to confine themselves into hadrons, protons, neutrons, and other particles. This transition, called the quark-hadron transition, is one of the fundamental phase changes in the early universe's history. The matter we are made of, the protons in every atomic nucleus in your body, congealed out of free quarks at this moment. Before 1 microsecond, your protons did not exist. After it, they did. Going back further still, to before 10 to the power of -12 seconds, a picosecond, takes us into the electroweak epoch, when electromagnetism and the weak nuclear force were unified into a single electroweak interaction. The Higgs field had not yet acquired its non-zero value. Particles were massless. The 4 fundamental forces of nature that we observe today were fewer and less distinct. And before that lies the Planck epoch, the first 10 to the power of -43 seconds, called the Planck time, where quantum gravity effects become significant and our current theories simply break down. We do not have a working theory of quantum gravity. General relativity, which describes gravity on large scales, and quantum mechanics, which describes particles on small scales, are mutually inconsistent at the Planck scale. What happened in that first instant, if the concept of an instant even applies, is genuinely unknown physics. The wall the CMB places at 380,000 years is a practical observational limit, but physics itself places a deeper conceptual wall much earlier, at the Planck scale, where our equations lose their validity and our ability to even formulate meaningful questions about what was happening comes into question. Part 4. The Era the Fog Hides. 380,000 years of invisible history. Here is a number that deserves a moment of quiet attention. 380,000 years. That is the gap between the Big Bang and the surface of last scattering, the wall of the CMB, the oldest light we can detect. That is the interval of cosmic history for which we have no direct photon-based observations whatsoever. And in that 380,000-year gap, that invisible epoch between the Planck scale at the beginning and the moment the universe went transparent, some of the most consequential events in the entire history of reality took place. Let us walk through that era slowly, because it deserves more than a summary. Its structure, and what we know and do not know about it, is the story of what hides behind the wall. For the first approximately 10 to the power of -36 seconds, the universe is believed to have undergone inflation. This is the theory, first developed by Alan Guth in 1981 and refined by André Linde, Paul Steinhardt, and many others, that the universe expanded exponentially, doubling in size repeatedly, at an almost incomprehensible rate, in an extremely brief period, driven by the potential energy of a quantum field called the inflaton. The inflationary expansion is thought to have taken the universe from a size vastly smaller than a proton to something on the order of a marble in a time shorter than 10 to the power of -32 seconds. The mathematics of this expansion, a volumetric increase of at minimum 10 to the power of 78, would smooth out any spatial curvature, making the universe appear geometrically flat. It would take what started as a tiny causally connected region and expand it to a volume much larger than the observable universe today, explaining why regions of the CMB that appear causally disconnected have the same temperature. It would dilute any exotic particles, magnetic monopoles, or other relics of high-energy physics to unmeasurably low densities. Inflation explains, in one theoretical stroke, several of the most puzzling large-scale properties of the universe. Why is the universe so geometrically flat? Inflation stretched away the curvature. Why is the CMB so uniform in temperature across regions that, in a non-inflationary universe, could never have been in causal contact? Inflation expanded a single thermally equilibrated region to encompass everything we can see. But inflation also did something subtler and more profound. As the inflaton field drove this exponential expansion, quantum fluctuations in the field, tiny, random, quantum mechanical perturbations, were stretched by the expansion from microscopic scales to macroscopic ones. A quantum fluctuation that would normally have been a transient, subatomic scale variation in energy density was blown up to the scale of galaxies, galaxy clusters, and eventually the large-scale structure of the entire cosmos. These stretched quantum fluctuations became the seeds of all subsequent cosmic structure, the slight overdensities around which matter would later gravitationally collect to form galaxies. The tiny temperature variations we see in the CMB, those 1 part in 100,000 fluctuations, are the grown-up versions of quantum fluctuations from the inflationary era. The very specific statistical pattern of those fluctuations, specifically the near-scale invariant spectrum first predicted by inflation, matches the observations with striking accuracy. This is circumstantial evidence for inflation that most cosmologists find compelling. But inflation has never been confirmed directly. We do not know what the inflaton field is made of, whether it is a fundamental scalar field or a composite of something more complicated, or whether inflation happened as the standard model describes or in some variant form. And most fundamentally, we do not know what happened before inflation, whether the word before even makes sense, or what triggered the inflationary phase in the first place. After inflation ended, the universe underwent a period called reheating, in which the energy stored in the inflaton field was transferred into a hot thermal bath of elementary particles. The universe transitioned from the cold, exponentially expanding state of inflation into the hot, radiation-dominated plasma of the standard Big Bang model. What happened at the end of inflation, how the energy was transferred, what particles were produced, and in what proportions, determines the initial conditions for everything that followed. Then came the quark-gluon plasma era, which we have already discussed, the quark-hadron transition, Big Bang nucleosynthesis, and then a long, quiet period, from about 20 minutes to 380,000 years, in which the universe was simply expanding and cooling, a plasma of protons, electrons, and photons slowly cooling toward the temperature at which neutral atoms could form. This period is called the photon epoch, and it is almost entirely opaque to direct observation. The universe during the photon epoch was radiatively dominated. Photons contributed more to the total energy density than matter. The plasma was in near-perfect thermal equilibrium, which means that each small region looked almost identical to every other small region. The acoustic oscillations were running, structure was building at the quantum level, but no photon could escape to tell us about it from the inside. This is the invisible era, 380,000 years of cosmic history for which we have no direct photon record. The wall hides everything. Part 5. What the wall actually tells us. The information locked in frozen sound. The cosmic microwave background is not just a barrier. To say that and leave it there would be the equivalent of calling a library a pile of paper. The CMB is one of the most information-dense scientific datasets in the history of human inquiry. Every feature of the temperature map, every peak and trough in the power spectrum, every subtle polarization pattern in the polarized components of the radiation encodes specific physical quantities about the early universe with a precision that no other cosmological probe can match. Let us talk about what is actually locked in that frozen map of the last scattering surface. The temperature of the CMB, 2.725 Kelvin, is itself a measurement of cosmic history. It represents the current temperature of the universe's photon bath, stretched by a factor of roughly 1,100 from the 3,000 Kelvin temperature of the plasma at recombination. Every time the universe doubled in size, the wavelength of the CMB photons doubled along with it, and their temperature halved. So the current temperature encodes, directly, how much the universe has expanded since 380,000 years ago. The acoustic peaks in the CMB power spectrum are perhaps the most information-rich feature. When the acoustic oscillations in the plasma froze at recombination, they imprinted a specific pattern on the temperature fluctuations. Regions where the oscillation was at its maximum compression at that moment show up as hot spots. Regions at maximum rarefaction show up as cold spots. The specific angular sizes of those hot and cold spots, how large they appear on the sky, depend on three things: the physical size of the sound horizon at the time of recombination, the distance from us to the last scattering surface, and the geometry of the space through which the light has traveled. If space is flat, the apparent angular sizes come out one way. If space is curved, they come out differently. From the measured angular positions of the acoustic peaks, we know that the universe is very close to geometrically flat. The total energy density of the universe is within a fraction of a percent of the critical density, the precise value at which the universe's expansion balances its own gravitational self-attraction. This is a remarkable fact. The universe, for reasons that inflation can partially explain but not fully account for, sits at exactly the balance point between eventual gravitational recollapse and eternal expansion. The relative heights of the successive acoustic peaks, the first peak, the second, the third, and further harmonics, depend on the ratio of ordinary baryonic matter to photons in the plasma. A universe with more baryons relative to photons produces a different pattern of peak heights than one with fewer. From those peak heights, the Planck satellite has measured the baryon density to a precision better than 1%, finding that ordinary matter, everything made of protons and neutrons, including every atom in every star in every galaxy, constitutes only about 4.9% of the total energy content of the universe. The presence of dark matter, which interacts gravitationally but not electromagnetically, affects the acoustic oscillations differently from baryonic matter. Dark matter falls into gravitational potential wells and deepens them, but it does not participate in the acoustic oscillations the way baryonic matter does. The specific way dark matter modifies the pattern of CMB fluctuations has been measured so precisely that we know dark matter constitutes about 26.8% of the universe's energy content. What dark matter is, which particle or particles it consists of, whether it has any interactions beyond gravity, remains unknown, but that it exists in roughly that proportion is as secure as any measurement in modern cosmology. The CMB also carries information about the polarization of its photons, the specific orientation of the electric field oscillations in the radiation. Polarization patterns in the CMB come in two types: curl-free patterns called E-modes, generated by the acoustic oscillations, and curl-type patterns called B-modes. B-modes can be generated by two things: gravitational lensing of E-modes as the CMB passes through the large-scale structure of the universe, and primordial gravitational waves generated during inflation. The detection of a primordial gravitational wave B-mode signal in the CMB would be a direct confirmation of inflation, the most sought-after signal in modern cosmology. As of 2026, no definitive primordial B-mode signal has been detected, though experiments including Bicep-Keck Array and the Simons Observatory are actively searching. There is one more thing the CMB tells us, and it is perhaps the most quietly profound. When you look at the CMB, when you take in that map of the last scattering surface with all its temperature variations, you are looking at the largest scale structure of the universe. The CMB is not just a signal from long ago, it is a boundary condition. It specifies, with extraordinary precision, the state of the universe at 380,000 years, from which everything subsequent follows in a chain of physical causation that is, in principle, calculable. The galaxies you see in the night sky, the Milky Way, the Andromeda Galaxy, the distant clusters of galaxies visible as faint smudges, all of them were, at 380,000 years, subtle overdensities in the nearly uniform plasma, regions where the matter density was perhaps 1 part in 100,000 higher than average. Over 13.8 billion years of gravitational amplification, those tiny seeds grew into the vast structures of the cosmic web. The particular pattern of galaxies in the universe today is, in a very direct physical sense, the CMB pattern grown up. The wall tells us where we came from, but it does not tell us what preceded it. Part 6. The messengers that could slip through, the ghost particles. There is a particle that was present at the creation. It was there when the universe was 1 second old, filling every cubic centimeter of space at temperatures of 10 billion Kelvin, colliding constantly with electrons and protons, carrying energy and momentum throughout the primordial plasma. And then, at that 1 second mark, something happened. The universe cooled just enough, and the density dropped just enough, that the interaction rate between these particles and ordinary matter fell below the expansion rate of the universe. The particles stopped interacting. They decoupled from everything around them. And they have been traveling freely through the universe ever since, passing through stars, through planets, through the entire apparatus of the cosmos, interacting with almost nothing. These are neutrinos. Specifically, they are what cosmologists call the cosmic neutrino background, the relic neutrinos left over from the Big Bang, the neutrino equivalent of the CMB. To understand how extraordinary the cosmic neutrino background is, as a potential window past the CMB wall, you need to understand what decoupled means in this context. The CMB photons decoupled at 380,000 years, when the universe became transparent to light. But the neutrinos decoupled much earlier, at approximately 1 second after the Big Bang. That means neutrinos carry information about the state of the universe 379,999 years before the CMB was released. If we could detect the cosmic neutrino background in detail, we would have a direct snapshot of the universe at 1 second old. We would pierce the wall and reach almost to the beginning. The cosmic neutrino background is estimated to have a temperature today of approximately 1.95 Kelvin, slightly cooler than the CMB's 2.725 Kelvin. This difference arises because, slightly after neutrino decoupling, the electron-positron pairs in the primordial plasma annihilated each other, transferring their energy to the photons and heating the photon bath slightly relative to the neutrinos. The neutrino background and the photon background have been at slightly different temperatures ever since. The cosmic neutrino background is not hypothetical. Its existence is firmly established by indirect evidence. The number of neutrino species, specifically how many types of light neutrinos exist, affects the expansion rate of the universe during Big Bang nucleosynthesis. More neutrino species means faster expansion, which means nucleosynthesis proceeds at a different rate and produces a different ratio of helium to hydrogen. The observed helium abundance matches a universe with approximately 3 neutrino species, exactly what the standard model of particle physics predicts. The imprint of the cosmic neutrino background on the CMB power spectrum has also been measured, in the specific way that neutrinos suppress small-scale matter perturbations. The neutrinos are there, we just have not seen them directly. Detecting relic neutrinos directly is, by a substantial margin, the hardest experimental challenge in physics. The problem is their energy. The cosmic neutrino background photons have been redshifted to an average energy of about 0.0002 electron volts, a factor of roughly 5 billion times lower energy than the CMB photons, and incomparably lower than the high-energy cosmic neutrinos that experiments like IceCube detect routinely. At such low energies, neutrinos interact with matter at a rate so feeble that a relic neutrino could pass through a light-year of solid lead, with only an even chance of being stopped. There is exactly one experimental proposal serious enough, technically advanced enough, and physically credible enough to have a genuine shot at detecting the cosmic neutrino background in the foreseeable future. It is called Ptolemy, the Princeton Tritium Observatory for Light, Early Universe, Massive Neutrino Yield, and it represents one of the most ambitious detector physics programs ever conceived. The detection principle of Ptolemy relies on a process called neutrino capture on tritium. When a neutrino is absorbed by a tritium nucleus, the tritium undergoes a conversion to helium-3, emitting an electron in the process. The energy of that electron is slightly higher than the energy of electrons emitted in ordinary tritium beta decay, by a tiny margin equal to the mass energy of the neutrino. If Ptolemy can measure the endpoint energy of tritium beta decay with sufficient precision, and if the neutrino mass is large enough relative to the energy resolution, the capture of cosmic relic neutrinos should appear as a peak in the electron energy spectrum just above the ordinary beta decay endpoint. The experimental challenges are severe. The required energy resolution is at the level of 0.1 to 0.2 electron volts, which requires cryogenic calorimeters operating near absolute zero. The tritium target needs to be spread across a large area in an extremely thin, uniform layer on a graphene substrate to minimize energy broadening from thermal motion. Background rejection requires extraordinary measures. The rate of relic neutrino capture with 100 grams of tritium is predicted to be only about 9 events per year, sitting against a much larger background of ordinary beta decay electrons. A small-scale prototype of Ptolemy has been operating at the Princeton Plasma Physics Laboratory, and the collaboration has been publishing steady progress reports on the technical challenges of building the full detector. If Ptolemy or a successor experiment successfully detects the cosmic neutrino background, and this is a significant if, dependent on neutrino masses and technology advances, it would open a window onto the universe at 1 second old, a direct observational snapshot 380,000 years before the CMB wall. The implications for cosmology and particle physics would be profound. The neutrino background carries information about the number of neutrino species, their masses, and the conditions in the primordial plasma that are inaccessible through any other means. But even the cosmic neutrino background has a wall of its own. Neutrinos interact so rarely that relic neutrinos from before, about 1 second, when the universe was hot enough that even neutrino interactions were frozen out by the extreme conditions, would be even harder to detect. And at the very earliest times, even neutrinos were in thermal equilibrium with the rest of the primordial plasma, making them equally opaque to observation from the outside. To truly see past every plasma wall every thermal equilibrium barrier, you need something that does not interact through any force except gravity. You need gravitational waves. Part 7. Ripples from before time. Gravitational waves as the ultimate messenger. When Albert Einstein published his general theory of relativity in 1915, the equations predicted the existence of gravitational waves, ripples in the fabric of spacetime itself, propagating at the speed of light, carrying energy and information about whatever cataclysm produced them. Einstein himself was not sure whether they were real physical phenomena or mathematical artifacts of his coordinate system. It took a century and detectors of almost science-fictional sensitivity to prove that they were real. On September 14, 2015, the twin detectors of the Laser Interferometer Gravitational Wave Observatory detected a ripple in spacetime produced by two black holes, each roughly 30 times the mass of the Sun, spiraling together and merging approximately 1.3 billion light-years away. The entire gravitational wave signal lasted about a fifth of a second. The stretching and compression of spacetime that the LIGO detectors measured was smaller than 1,000th the diameter of a proton, and it unambiguously confirmed one of the great predictions of general relativity. But the black hole mergers that LIGO detects are, from a cosmological perspective, relatively recent events. They tell us about the behavior of matter in the current universe, not the conditions of the early one. The truly transformative potential of gravitational wave astronomy lies in an older, fainter, and far more diffuse signal, the stochastic gravitational wave background produced in the early universe. Gravitational waves, unlike photons and unlike even neutrinos, interact with matter only through gravity, the weakest of the four fundamental forces by an enormous factor. A gravitational wave passes through ordinary matter as if ordinary matter were not there. Planets, stars, galaxies, the dense plasma of the early universe, none of these provide any significant barrier to gravitational wave propagation. This means that primordial gravitational waves, produced in the first fractions of a second after the Big Bang, have been traveling freely through the universe ever since, carrying information about whatever conditions produced them. There are several theoretical mechanisms for generating primordial gravitational waves in the early universe. The most eagerly anticipated is inflation itself. During the inflationary epoch, the same quantum fluctuations that seeded the density perturbations we see in the CMB also generated tensor perturbations, fluctuations in the geometry of spacetime itself. These tensor perturbations evolve into a stochastic background of gravitational waves with a specific spectrum that depends on the energy scale of inflation and the exact mechanism by which inflation occurred. Detecting this inflationary gravitational wave background would confirm inflation and constrain its energy scale with a precision that no other observation can provide. The B-mode polarization pattern of the CMB that experiments like Bicep-Keck array are searching for is, in essence, the indirect imprint of these inflationary gravitational waves on the photon background. But there is also the prospect of directly detecting the gravitational wave background itself with next-generation interferometers. The planned Laser Interferometer Space Antenna, known as LISA, is a space-based gravitational wave detector consisting of 3 spacecraft flying in a triangular formation with arms 2.5 million kilometers long. LISA is designed to detect gravitational waves at frequencies much lower than ground-based detectors like LIGO, in the millihertz range, which is precisely where many cosmological sources of gravitational waves are expected to produce their strongest signals. Phase transitions in the early universe, networks of cosmic strings, and various exotic astrophysical sources all produce gravitational wave backgrounds in LISA's frequency band. In 2023, the North American Nanohertz Observatory for Gravitational Waves, NanoGrav, together with other pulsar timing array collaborations around the world, announced the detection of a stochastic gravitational wave background in the nanohertz frequency range. Pulsar timing arrays use the extraordinary rotational stability of millisecond pulsars, neutron stars that spin hundreds of times per second with a precision that rivals atomic clocks, as a galactic-scale gravitational wave detector. When a gravitational wave passes between us and a pulsar, it subtly distorts the spacetime through which the pulsar's radio signals travel, causing barely detectable shifts in the arrival times of those signals. The nanograv signal is most likely produced by a population of supermassive black hole binaries throughout the universe, pairs of black holes containing millions to billions of solar masses, orbiting each other at galactic centers and slowly spiraling together over millions of years. But there is a possibility, which researchers are actively investigating, that some portion of the signal has a cosmological origin. The specific spectral shape of the background, how its amplitude varies with frequency, carries information about its source, and the currently observed spectrum is not perfectly consistent with a pure astrophysical origin. If future pulsar timing array measurements or LISA detections reveal a gravitational wave background with clear cosmological characteristics, a spectrum that matches predictions for a first-order phase transition in the early universe, or cosmic string oscillations, or the inflationary tensor spectrum, the implications would be extraordinary. We would have a direct observational window into the early universe that predates the CMB by orders of magnitude. Depending on the specific source, gravitational wave backgrounds could potentially carry information from as early as the electroweak phase transition at 10 to the power of -12 seconds, or even from the end of inflation at 10 to the power of -32 seconds. Gravitational waves are the ultimate messenger. They pass through plasma, through matter, through the entire history of cosmic evolution without being absorbed, scattered, or significantly altered. If primordial gravitational waves were produced in the early universe in detectable quantities, they are still here, propagating through the cosmos right now, and with sufficiently sensitive detectors, we could read their message directly from the source. The wall that blocks photons does not block gravitational waves. The wall that eventually blocks neutrinos does not block gravitational waves either. Gravitational waves are the key that could, in principle, unlock the door behind the CMB wall and give us direct observational access to epochs of cosmic history that no other tool can reach. Part 8. Matter versus antimatter, the most fundamental question behind the wall. Of all the mysteries hidden behind the CMB wall, one stands above the others in its directness and its implications. It is not a subtle question about the spectral shape of a gravitational wave background or a technical challenge in energy resolution for a neutrino detector. It is the most basic question you could ask about the universe in its current form. Why does anything exist? This is not a philosophical provocation. It is a precise physical question, and it has a precise physical answer that we do not currently possess. According to the standard model of particle physics, every fundamental particle has an antiparticle, a partner with the same mass but opposite charge, and other quantum numbers. An electron has a positron. A proton has an antiproton. A quark has an antiquark. When matter and antimatter meet, they annihilate each other completely, converting all of their mass into energy in the form of photons. The mathematics of the standard model predicts that the Big Bang should have produced matter and antimatter in essentially equal quantities. Not exactly equal, the laws of physics allow for a small difference between matter and antimatter through a subtle asymmetry called CP violation, but equal to an extraordinarily high degree. If matter and antimatter had been produced in perfect equality, they would have annihilated each other completely in the early universe. Every proton would have found an antiproton. Every quark would have found an antiquark. The entire material content of the universe would have converted itself into photons, and the universe today would be an expanding sea of radiation, with no atoms, no stars, no galaxies, no planets, no life, and no one to ask why. This did not happen. You exist. The fact of your existence is direct evidence that something broke the symmetry between matter and antimatter in the early universe. The asymmetry that survived is tiny. Current measurements of the cosmic microwave background and Big Bang nucleosynthesis indicate that the baryon asymmetry parameter, the ratio of baryons to photons in the universe, is approximately 6 times 10 to the power of -10. That is 0.0000000006. For every 10 billion matter-antimatter pairs that annihilated in the first second of the universe, only one baryon survived. 1 in 10 billion. That single survivor is responsible for every atom in every star, in every galaxy, in the observable universe. Every atom in your body was, in a very literal sense, the winning ticket in a lottery, where the odds were 10 billion to 1 against. The physical process that generated this asymmetry is called baryogenesis, and it is one of the most important unsolved problems in theoretical physics. The Soviet physicist Andrei Sakharov identified in 1967 3 conditions that must be satisfied for baryogenesis to occur. First, baryon number violation. There must be some physical process that can change the number of baryons in the universe, creating an excess of matter over antimatter. Second, CP violation. The laws of physics must treat matter and antimatter differently in some respect. Third, departure from thermal equilibrium. The asymmetry must be generated at a time when the universe was not in perfect thermodynamic equilibrium, because equilibrium conditions would erase any asymmetry as fast as it was created. All 3 Sakharov conditions can, in principle, be satisfied in various theoretical frameworks. The Standard Model itself satisfies all 3 in a limited way. It has baryon number violation through quantum mechanical effects at high energy, it has CP violation in the weak interaction sector, and the electroweak phase transition in the early universe was a departure from equilibrium. But when you calculate how much baryon asymmetry the Standard Model actually produces through these mechanisms, the answer is far smaller than the observed asymmetry. The Standard Model's CP violation is insufficient by many orders of magnitude to account for the universe we observe. This is one of the primary reasons physicists know the Standard Model is incomplete. There must be physics beyond the Standard Model. New particles, new interactions, new sources of CP violation that are responsible for baryogenesis. And the clues to what that physics is are encoded in the conditions of the early universe, in the era before the CMB wall, where baryogenesis actually occurred. Various theoretical mechanisms have been proposed. Electroweak baryogenesis suggests that a strongly first-order electroweak phase transition, with additional sources of CP violation from new particles beyond the Standard Model, could have generated the observed asymmetry. But the Higgs boson, discovered at CERN in 2012 at a mass of about 125 GeV, is too heavy for this mechanism to work within the minimal Standard Model. The electroweak phase transition with the observed Higgs mass is a smooth crossover, not a sharp first-order transition. Leptogenesis is a more speculative but widely studied alternative. In leptogenesis, the asymmetry between matter and antimatter is first generated in the lepton sector, the sector of electrons, muons, taus, and neutrinos, through the CP-violating decays of very heavy right-handed neutrinos that are postulated to exist but have not yet been observed. This lepton asymmetry is then partly converted into a baryon asymmetry through processes called sphalerons that violate baryon and lepton number in the early universe. Leptogenesis is attractive theoretically and provides a deep connection between the matter-antimatter asymmetry of the universe and the properties of neutrinos, particularly their masses and mixing angles, which are themselves active areas of experimental investigation. Whatever the correct mechanism, the physics of baryogenesis occurred at very high energies and very early times, temperatures of 10 to the 15 Kelvin or above, times of 10 to the power of negative 35 seconds or earlier, well inside the era hidden by the CMB wall. The only way to probe the conditions of baryogenesis is through indirect evidence, the properties of neutrinos, searches for new sources of CP violation at particle accelerators, precision measurements of the CMB for signatures of a first-order phase transition, and the gravitational wave backgrounds that such a transition would have produced. Part 9. Inflation. The story before the story. If the CMB wall sits at 380,000 years, and the plasma fills the space between us and the wall all the way back to about 1 second, and the quark-gluon plasma fills the first microsecond, and the electroweak epoch fills the picosecond before that, then what fills the first 10 to the power of negative 36 seconds? What came before everything we can, even in principle, trace? The standard answer is inflation. And inflation is simultaneously the most successful and the most unsettling idea in modern cosmology. The horizon problem and the flatness problem are the two observational facts that most forcefully demand inflation. The horizon problem asks, why is the CMB the same temperature in every direction to 1 part in 100,000? In a non-inflationary Big Bang model, regions of the CMB that are separated by more than about 2 degrees on the sky were never in causal contact. They could never have exchanged information, never have thermalized to the same temperature, because no signal traveling at the speed of light could have passed between them in the time available. And yet they are the same temperature to extraordinary precision. The universe looks like it was thermalized, like it had time to reach equilibrium. But in the standard model without inflation, it did not have time. The flatness problem is equally puzzling. The geometry of space depends on the total energy density relative to a critical value. If the energy density is above the critical value, space is positively curved. If below, it is negatively curved. If exactly equal, it is flat. Observations tell us the universe is flat to within about 0.5%. In a non-inflationary cosmology, the flatness of the universe at the present epoch requires that the energy density at early times was tuned to equal the critical density to an extraordinary precision, 1 part in 10 to the 60 near the Planck epoch. Any deviation from flatness at those early times would have grown, and a universe that started even slightly curved would have either collapsed or expanded into empty space long before galaxies could have formed. Inflation solves both problems elegantly. If the early universe underwent a period of exponential expansion, a tiny causally connected region was stretched to a size much larger than the observable universe today, explaining why everything we can see was once in equilibrium, and the exponential expansion stretched any initial spatial curvature to near-perfect flatness, the way inflation of a balloon makes its surface locally flat even if the balloon's overall shape is curved. But inflation has a deeper contribution that is perhaps even more fundamental. The quantum fluctuations during inflation, the tiny random perturbations in the inflaton field, were stretched from sub-Planck scales to macroscopic scales by the exponential expansion. These stretched quantum fluctuations became the seeds of all large-scale structure. The slight density variations that grew into galaxies, galaxy clusters, and the vast network of cosmic filaments and voids that organizes the matter of the universe on the largest scales. In the most profound interpretation, inflation transforms quantum uncertainty into cosmic structure. The exact position of a galaxy cluster in the universe today is, in principle, traceable back to a quantum fluctuation in the first fraction of a second of time. The cosmos we inhabit is not a deterministic system that followed inevitably from classical initial conditions. It is the macroscopic manifestation of quantum randomness, amplified over 13.8 billion years. The evidence for inflation is compelling but indirect. The nearly scale-invariant spectrum of primordial fluctuations, the prediction that fluctuations of different sizes should be approximately equal in power, matches the CMB observations precisely. The flatness of the universe is consistent with inflation's prediction. The absence of magnetic monopoles and other relics of phase transitions in the very early universe is naturally explained by inflation's dilution of any pre-existing exotic particles. But inflation has never been directly confirmed. The inflaton field, the quantum field whose potential energy drove the exponential expansion, has not been identified with any known particle. The energy scale at which inflation occurred is not known. There are dozens of competing inflationary models, ranging from simple single-field models to complex multi-field scenarios, and the CMB data currently available is consistent with a wide range of them. The detection of a primordial B-mode polarization signal in the CMB would substantially narrow the field, but even that would not uniquely identify the inflationary model. There is a deeper concern about inflation that some physicists take seriously. In most inflationary models, inflation does not end everywhere at once. Different regions of the inflationary universe exit the inflationary phase at different times, and the regions that do not exit become an eternally inflating background, a never-ending expansion that produces new bubble universes, each with potentially different physical properties, in a process called eternal inflation. If eternal inflation is real, our universe is just one of an incomprehensibly large number of bubble universes, each nucleated from the inflating background. This is the multiverse, a concept that is scientifically contentious because it is, in its most general form, untestable. Whether inflation is correct, whether eternal inflation occurs, whether the multiverse is real, these are questions the CMB wall makes inaccessible to direct observation. They are part of the story before the story, the era before the wall, the region where our best theory currently lives but cannot be directly confirmed. Part 10. What lies beyond the observable universe? At this point, we should separate two distinct concepts that are often confused. The CMB wall, the surface of last scattering at 380,000 years, is not the edge of the universe. It is the edge of what we can see. These are very different things, and confusing them leads to a fundamentally mistaken picture of reality. The observable universe is a sphere centered on Earth, with a radius of approximately 46.5 billion light-years. This is larger than 13.8 billion light-years, the age of the universe times the speed of light, because the universe has been expanding during the time it took the light to reach us. The most distant photons we can detect are the CMB photons, which were emitted when the universe was 380,000 years old. By the time those photons have reached us, the regions of the universe from which they were emitted have been carried by cosmic expansion to a current distance of approximately 46.5 billion light-years. Beyond 46.5 billion light-years, there is simply no time for light to have reached us since the Big Bang. But that does not mean there is nothing there. The universe is almost certainly much larger than the observable portion. How much larger depends on cosmological details about the global topology and geometry of space. From the flatness of the universe measured by the CMB, we know that if the universe has positive curvature, like the surface of a sphere in 4 dimensions, the radius of curvature is at least several orders of magnitude larger than the observable universe. In some inflationary models, the entire inflated region could be so much larger than the observable universe that the rest of the universe would be, for all practical purposes, infinite. In a spatially flat or negatively curved infinite universe, there would be no edge in the sense of a physical boundary, just an ever-receding horizon of what we can observe, determined purely by the finite speed of light and the finite age of the universe. Beyond our particle horizon, the boundary of the observable universe, there are regions that look, as best we can tell, just like ours. The same physical laws, the same types of particles, the same chemistry. In an infinite universe with a finite number of possible quantum states, there would be exact copies of every configuration that exists in our observable region, including exact copies of you, reading or listening to this, in configurations identical to the present moment. This is not science fiction or philosophy. It is a mathematical consequence of infinity. In an infinite universe, every finite configuration repeats infinitely many times. Whether or not the universe is infinite is not currently knowable with certainty. The topology of space, whether it is simply connected like infinite flat space or has a more complex shape that loops back on itself like a finite torus, cannot be determined from CMB observations if the scale of any topological identification is larger than the observable universe. Future measurements might reveal subtle patterns in the CMB that would indicate we are seeing the same region of space from multiple directions, which would imply a finite but unbounded universe. But if the universe is much larger than what we can observe, even this search would be inconclusive. The particle horizon is one kind of wall. The CMB wall is another, different kind, and beyond both of them lies a universe whose extent, whose structure, and whose relationship to the observable portion is genuinely unknown, in a way that is not merely a technical limitation, but a fundamental consequence of the speed of light and the age of time. Part 11. The wall physics built around itself, the limits of knowledge. There is a deeper wall than the CMB, a wall that is not made of plasma or photons or any physical substance at all. A wall built not by the physics of the early universe, but by the structure of physical law itself. It is the wall of initial conditions. Physical theories, in their most fundamental form, are equations that describe how a system evolves from one state to another. Given the state of a system at one moment in time and the laws that govern its evolution, you can in principle calculate its state at any other moment. General relativity tells you how space-time curves in response to the distribution of matter and energy, and how that curvature in turn affects the motion of matter and energy. Quantum mechanics tells you how quantum fields evolve, how probabilities for particle interactions depend on field configurations, and how measurements force quantum systems to choose definite outcomes. These are extraordinarily powerful frameworks, but they all take initial conditions as inputs, not as outputs. General relativity can tell you how the universe evolved from the conditions at 380,000 years to the conditions today with exquisite precision, given those initial conditions from the CMB. It cannot tell you why those initial conditions were what they were. It cannot tell you why the density perturbations had the specific amplitude they had, why the baryon to photon ratio was 6 times 10 to the power of -10, rather than some other value, why the universe had almost exactly the critical density rather than slightly more or less. Inflation pushes this problem back further. It explains why the universe at 380,000 years had the properties it had, in terms of the properties of the inflaton field at the beginning of inflation. But it cannot explain why the inflaton field had those properties. It takes its own initial conditions as given and evolves forward from them. At the Planck scale, 10 to the power of -43 seconds and 10 to the power of 19 GeV, quantum gravity effects become dominant, and our current theoretical frameworks break down entirely. This is not a matter of insufficient calculation. It is a fundamental incompatibility between general relativity and quantum mechanics that has resisted resolution for nearly a century. General relativity treats spacetime as a continuous, smooth, deterministic background that curves in response to matter. Quantum mechanics requires that any system described quantum mechanically must have quantized states, uncertainty principles, and superposition. When you apply quantum mechanics to spacetime itself, the equations produce infinities that no known regularization procedure can make physically meaningful. Various approaches to quantum gravity have been proposed. String theory, loop quantum gravity, causal dynamical triangulations, and others each attempt to provide a consistent description of physics at the Planck scale. But none of them has yet made a confirmed experimental prediction that distinguishes it from the others, and none provides a complete answer to the question of the initial conditions of the universe. The Hartle-Hawking no-boundary proposal, developed by James Hartle and Stephen Hawking in the 1980s, suggests a potential way to talk about the initial conditions of the universe without an actual initial moment in time. In their formulation, using a mathematical technique called a Euclidean path integral over geometries, the universe has no boundary in time. Time itself becomes smoothly rounded off at the beginning, in the same way that the surface of the Earth has no edge at the South Pole, even though the South Pole is a definite geometric feature. In this picture, asking what happened before the Big Bang is like asking what is south of the South Pole. The question is malformed. Time simply does not extend in that direction. But the Hartle-Hawking proposal has its own difficulties. It does not clearly predict the specific initial conditions of our universe. It admits multiple possible initial states, and selecting among them requires additional principles that are not yet established. And it is formulated in terms of Euclidean quantum gravity, a mathematical trick of analytically continuing time to imaginary values, whose physical interpretation is deeply controversial. There is also the anthropic argument, the suggestion that we should not be surprised to find ourselves in a universe with initial conditions compatible with the existence of observers, because only such universes contain observers to be surprised. This argument, associated with Brandon Carter, Steven Weinberg, and the broader anthropic principle literature, has real logical force, but also deep problems. In its most ambitious form, the anthropic principle requires a multiverse, an ensemble of universes with different initial conditions and physical constants, to give it statistical content. Without such an ensemble, Saying the universe must have observer-compatible initial conditions is simply a restatement of the observation, not an explanation. The wall at the beginning of time is arguably the most fundamental wall in all of physics. It is not the wall of the CMB, which hides 380,000 years of early cosmic history from our electromagnetic observations. It is the wall at the very beginning, beyond which the concept of time may not apply, our current laws do not function, and the question of what determined the starting conditions of everything may be unanswerable within any framework we currently possess. Part 12. The information hiding in plain sight. What CMB anomalies might tell us. Before we look to the future, there is one more aspect of the CMB wall that deserves close attention. Not what lies beyond it, but what we have already found written in it that we do not yet fully understand. The standard cosmological model fits the CMB data almost perfectly, but almost perfectly is not perfectly. There are features in the CMB that sit at the edge of statistical significance, features that might be noise, might be systematic artifacts of the measurement, or might be telling us something genuinely new about the early universe, or the physics beyond the wall. The most discussed of these anomalies is the hemispherical power asymmetry. The CMB should look statistically the same in every direction. The cosmological principle demands it. But analysis of the Planck satellite data reveals a subtle asymmetry. The power in CMB fluctuations on large angular scales is slightly higher in one hemisphere of the sky than in the opposite hemisphere. The effect is statistically significant at roughly the 3 sigma level, notable but not conclusive. It could be a rare statistical fluctuation in a random process. It could be a systematic instrumental effect. Or it could be a genuine asymmetry in the primordial power spectrum, pointing to an inflationary model with a preferred direction, or perhaps to a non-trivial topology of the universe. There is also the cold spot, a region in the CMB centered roughly in the southern celestial hemisphere that is noticeably colder and larger than would be expected by chance. Analysis suggests the cold spot occurs with a probability of only about 1 in 100 in a standard cosmological model. Some researchers have proposed it is the imprint of a supervoid, an enormous underdense region in the universe through which the CMB photons passed and lost energy, and there is indeed a large-scale void in the galaxy distribution in roughly the right direction. Others have proposed exotic explanations, including the imprint of a collision between our universe and another bubble universe in an eternally inflating multiverse. The alignment of the largest-scale CMB fluctuations, the so-called axis of evil, an unfortunate but memorable name given to the observation that the quadrupole and octupole components of the CMB appear to be aligned with each other and with the ecliptic plane, is another anomaly that has been discussed extensively. In a universe that obeys the cosmological principle, there should be no special axis. The alignment with the ecliptic could indicate a systematic effect related to the solar system, a known source of microwave emission that must be subtracted from the data, or it could indicate something genuinely cosmological. None of these anomalies has been established as a definitive violation of the standard model, but they are persistent. They appear in multiple independent analyses, they survive many systematic checks, and they collectively suggest that the universe at the largest observable scales might have features that our standard model does not fully account for. If even one of them turns out to be real, the implications for our understanding of inflation, the global topology of the universe, or the physics of the very early cosmos would be significant. This is the other way to try to see past the wall, not with new messengers, but with more careful reading of the map we already have. Every subtle pattern in the CMB, every deviation from the predictions of the standard model, carries information about the initial conditions that the standard model does not explain. The wall is made of this information, and we are still learning to read it. Part 13. The Future of Seeing the Unseeable. We are, in the history of cosmology, at an early stage. The CMB was discovered accidentally in 1964 by Arno Penzias and Robert Wilson, who were trying to clean pigeon droppings off a microwave antenna and found an inexplicable background signal that could not be eliminated regardless of what they did. The first detailed map of the CMB was produced by the COBE satellite in 1992, revealing for the first time the temperature fluctuations at the level of 1 part in 100,000. The WMAP satellite refined those measurements dramatically between 2001 and 2010. The Planck satellite, operational from 2009 to 2013 and releasing data through 2020, brought CMB measurements to a level of precision that will require a new generation of experiments to improve upon significantly. That new generation is being built now. The Simons Observatory, now in operation in the Atacama Desert of Chile, at an altitude of roughly 5,190 meters, combines multiple telescope sizes and thousands of individual detectors to measure the CMB polarization with sensitivity several times greater than Planck. The CMB-S4 experiment, a ground-based CMB experiment, combining the resources of multiple institutions and several telescope sites, will deploy roughly 500,000 detector elements when complete, a 2-order-of-magnitude increase over Planck's detector count. These experiments are targeted at the B-mode polarization signal from primordial gravitational waves, the signature of inflation. If the inflationary gravitational wave amplitude is in the range predicted by the simplest inflationary models, CMB-S4 should detect it at high significance within the next decade. In space, the proposed LightBird satellite, a Japanese-led mission with international participation, is designed specifically to measure the CMB polarization over the full sky with sensitivity to the inflationary B-mode signal at a level 10 times better than current experiments. LightBird would either confirm the primordial B-mode signal or eliminate the simplest inflationary models by showing they overpredicted the gravitational wave amplitude. Either outcome would be a major advance. On the gravitational wave front, LISA, the Laser Interferometer Space Antenna, is a European Space Agency mission in development, targeting launch in the late 2030s. With its 3-spacecraft configuration and million-kilometer arms, LISA will be sensitive to gravitational waves from a wide variety of astrophysical and cosmological sources. Supermassive black hole binaries, extreme mass ratio in spirals, verification binaries in our own galaxy, and potentially cosmological stochastic backgrounds from phase transitions in the early universe. All of these are in LISA's science case. If the electroweak phase transition was first order in some extension of the standard model, LISA would have a strong chance of detecting the gravitational wave background it produced. The Einstein Telescope, a proposed European underground gravitational wave observatory with a 10-kilometer arm length and triangular geometry, and the Cosmic Explorer in the United States, a next-generation ground-based interferometer with 40-kilometer arms, represent the next step beyond LIGO and Virgo. These instruments, proposed for the 2030s and 2040s, would be sensitive to gravitational wave backgrounds from astrophysical sources well into the epoch of the first stars, and potentially to primordial backgrounds from the earliest cosmic epochs. Pulsar timing arrays will continue to accumulate data. As more pulsars are added to the arrays and timing baselines extend over longer periods, the sensitivity to gravitational wave backgrounds at nanohertz frequencies will improve dramatically. The Square Kilometer Array, an international radio telescope combining dishes across Africa and Australia with a combined collecting area of roughly 1 square kilometer, will dramatically expand the number of precisely timed pulsars available for gravitational wave astronomy. If the nanograv stochastic background has a cosmological component, the SKA should be able to characterize it. For neutrinos, the path to detecting the cosmic neutrino background is longer and less certain. Ptolemy's prototype is providing invaluable information about the technical challenges. The full-scale detector, 100 grams of tritium distributed across a large graphene surface, coupled to cryogenic calorimeters and electromagnetic filters, represents a formidable engineering challenge. But the physics community's understanding of what needs to be achieved is clear, and the technology continues to develop. Within the next 20 to 30 years, it is plausible that a Ptolemy-scale experiment will either detect the cosmic neutrino background or provide strong enough upper limits to constrain neutrino properties at a level relevant to the standard cosmological model. What might we learn from all of this? What would the next generation of observations reveal about the wall, and what lies beyond it? In the best-case scenario, which is also the scenario many physicists consider most likely given the current theoretical landscape, the next decade of observations would confirm inflation through the detection of primordial B-modes, constrain the inflationary energy scale to within a narrow range, detect signatures of physics beyond the standard model in the stochastic gravitational wave background, and begin to reveal the properties of the cosmic neutrino background through direct detection. This would give us observational reach to within the first microsecond of the universe. It would place constraints on baryogenesis mechanisms by identifying the energy scale and nature of the electroweak phase transition. It would tell us whether the universe's flatness is a coincidence of initial conditions or an inevitable consequence of a specific inflationary model. It would advance our understanding of dark matter and dark energy through their imprints on large-scale structure and the CMB. But even in this best case, the Planck wall, the absolute barrier at the beginning of time where quantum gravity effects dominate and our equations break down, would remain intact. The first 10 to the power of -43 seconds would remain beyond any observational reach. The question of why the universe had the initial conditions it had, rather than some other set of conditions, would remain open. Part 14. The silence before the first word. What lies at the very beginning? Let us be honest about something that the language of cosmology sometimes obscures. When cosmologists talk about the Big Bang, they are not describing an event they can observe or calculate from first principles. They are describing an extrapolation of current physics, general relativity and quantum field theory, backward in time, to conditions at which those theories begin to fail. The Big Bang singularity, the mathematical point at the beginning of the standard cosmological model where density and temperature diverge to infinity, is not a physical event. It is an indication that general relativity has been pushed beyond its domain of validity. It is like the way Newtonian mechanics predicts that an object can accelerate to infinite speed if you push it long enough. Not a real physical outcome, but a signal that the theory has been extrapolated into a regime where it does not apply. What actually happened at the very beginning, if beginning is even a concept that applies, is simply unknown. We do not have a theory of quantum gravity that would tell us how space-time itself behaves at densities so extreme that quantum mechanical fluctuations in the geometry of space become of order 1. Several competing approaches to quantum gravity, string theory, loop quantum gravity, and others, make different predictions about the physics at the Planck scale, but none has been tested experimentally, and the Planck scale is roughly 16 orders of magnitude beyond the reach of any particle accelerator. Loop quantum gravity, in particular, suggests something striking about the very beginning. In loop quantum gravity, space-time at the Planck scale is not a smooth continuum, but a discrete network of quantum geometrical structures, spin networks, in the technical language of the theory. At Planck densities, the standard singularity predicted by general relativity is replaced by a bounce. The contracting phase of a prior universe reaches a minimum size, a Planck scale quantum geometry, and bounces back into expansion. In this picture, our Big Bang was not a creation event, but a transition, the beginning of an expansion phase in a universe with a prior history. The speculative universe before our Big Bang, in loop quantum cosmology frameworks, might have been a contracting universe that collapsed to the Planck density and bounced. In string theory, the prior state might be a higher dimensional geometry. In Penrose's conformal cyclic cosmology, the prior state is the far future of a previous universe, in which all massive particles have decayed or been absorbed into black holes, leaving a universe of pure radiation that, at sufficiently late times, loses all memory of scale and connects smoothly to the beginning of the next cosmic cycle. These are speculative ideas. Some of them may be tested indirectly. Loop quantum cosmology, for example, predicts specific modifications to the inflationary perturbation spectrum that next-generation CMB experiments might be able to distinguish from standard inflation. Penrose's conformal cyclic cosmology predicts specific patterns of gravitational wave rings in the CMB from the evaporation of black holes in the previous universe, which some researchers claim to have found as anomalies in the Planck data, though the statistical significance and interpretation of those claimed signals is highly contested. But the deeper question, not just what happened at the beginning, but what determined that what happened would happen, and whether the concept of cause and effect even applies to the origin of spacetime itself, may be permanently beyond empirical access. Not because of technology limitations that might be overcome, but because any observation we could make would be an observation from within the universe, from within the causal structure that the initial conditions themselves created. There is a sense in which asking for an observational test of the initial conditions of reality is like asking for a photograph of the camera. Part 15. The Wall as a Mirror, What Our Ignorance Reveals. There is a certain temptation, when confronting the scale of what we do not know about the early universe, to feel that physics has failed, that despite centuries of progress, we are still standing at the foot of an impenetrable barrier, unable to see what lies on the other side. But that reading has things exactly backwards. The CMB wall is not a monument to failure, it is a record of success. The fact that we can precisely describe what the wall is made of, ancient photons released at 380,000 years from a thermal plasma at 3,000 Kelvin, redshifted by a factor of 1,100 to a temperature of 2.725 Kelvin, carrying the frozen imprint of acoustic oscillations in a fluid whose composition we have measured to sub-percent precision, represents an achievement of extraordinary intellectual ambition. We built theoretical frameworks, developed mathematical tools, launched satellites, built detectors, and accumulated data over decades to learn exactly why we cannot see past a certain point. There is a deeply human quality to that enterprise. We are creatures with finite senses, born on a planet in one galaxy among 2 trillion, living for decades in a universe that has been expanding for 13.8 billion years. And we have worked out, using instruments made of the same atoms that came from those first 3 minutes of Big Bang nucleosynthesis, the composition of the universe to percent-level accuracy, the age of the universe to better than 1% accuracy, the geometry of space to fraction of percent accuracy, and the location of a barrier in cosmic time that exists because the early universe was too hot for light to travel freely. We know exactly where the wall is. We know exactly what it is made of. We know what it tells us about conditions on the near side. We have identified the messengers, neutrinos and gravitational waves, that might eventually let us reach past it. We are building the instruments to search for those messengers with sensitivity that would have been considered impossible science fiction 30 years ago. What we do not know, the physics of the first second, the mechanism of baryogenesis, the nature of the inflaton, the conditions at the Planck epoch, the initial conditions of reality, is a precisely defined set of questions, located at specific positions in the history of the universe, pointing toward specific theoretical gaps that we have identified through the very precision of what we do know. The ignorance is not amorphous. It is the shadow cast by a very bright light. The wall at the edge of the visible universe is, in the end, a feature of the universe telling us something true about itself. It is the universe saying, before 380,000 years I was opaque. I was hot and dense and tightly coupled, and I did not let light travel freely. What happened in that era is encoded in me in indirect ways, in my composition, in my geometry, in the tiny temperature fluctuations on my oldest surface, in the gravitational waves that will eventually tell future instruments about my earliest moments. I am older than my oldest light. What I was before I became transparent is something you will have to infer, with patience and precision and tools not yet built, from the clues I have preserved for you. Every telescope that has ever pointed at the CMB, every cryogenic detector that has measured its temperature to another decimal place, every pulsar timing array that has listened for the faint rumble of primordial gravitational waves, all of them are attempts to answer that invitation. The universe has left us clues. We are slowly learning to read them. The wall is real. It is physical. It blocks every photon that was ever generated before 380,000 years after the Big Bang, and it will always do so. But it is not impenetrable, not by everything. The neutrinos and gravitational waves that pass through the plasma of the early universe still carry their ancient signatures. The acoustic oscillations frozen in the plasma at the moment of recombination still speak, in the pattern of galaxy clustering and CMB temperature maps. The baryon asymmetry preserved in every atom of ordinary matter is itself a record of conditions in the first microsecond that nothing else can replicate. The universe has not hidden its past completely. It has hidden it behind a wall of light that blocks our most familiar tool for seeing. But it has left other doors. Finding them, building instruments sensitive enough to open them, and reading the information they contain. This is the project that cosmology is engaged in right now, in laboratories and on satellites and in mathematical frameworks being developed by physicists who may not live to see their ideas confirmed. Somewhere behind the wall, in the first fraction of the first second of time, lies the answer to questions that every person who has ever looked up at a clear night sky has silently asked. Why is there something instead of nothing? Where did the matter in your body come from? What determined the rules by which the universe plays? The wall is between us and those answers, but we are, with every new observation, every new instrument, every new theoretical insight, building a ladder. We have not climbed past the wall yet, but we know it is there, and we know it is finite, and we know that the universe beyond it is not empty of information. It is full of it. And that knowledge, precise, hard-won, and pointing forward into questions we cannot yet answer, is its own kind of light, traveling outward from the surface of what we know into the darkness of what we do not. The universe has a wall. We are learning to see through it. If this one settled in with you the way it settled in for me while putting it together, consider leaving a like. It helps more people find these videos. And subscribe if you want to be here for the next one. We are just getting started. End of script, Part 16, The Dark Architecture, What the Wall Refuses to Explain About Dark Matter and Dark Energy. When the Planck satellite data confirmed that approximately 95% of the universe's energy content consists of things we cannot directly detect or identify, dark matter and dark energy, the response from the broader scientific community was a mixture of wonder and deep discomfort. Not because the numbers were wrong. The evidence for dark matter and dark energy is overwhelmingly strong, coming from independent lines of observation that cross-check each other in exquisite detail. The discomfort was because two of the three largest components of the universe are fundamentally mysterious, and the physics that must have established their properties is hidden behind the CMB wall. Dark matter leaves its signature in the CMB through its influence on the acoustic oscillations. Ordinary baryonic matter, protons and neutrons, interacts with photons electromagnetically. It participates in the acoustic oscillations. Dark matter does not interact electromagnetically. It falls into gravitational potential wells, deepening them, but it does not feel the photon pressure that drives the oscillations. This difference shows up in the specific pattern of the acoustic peaks. The ratio of the first to the second peak in the CMB power spectrum is sensitive to the amount of dark matter, because dark matter enhances the gravitational pull that drives the compression phase of the oscillation without contributing to the radiation pressure that drives the expansion phase. From the Planck 2018 data release, dark matter constitutes 26.8% of the universe's energy density. This is 5 times more than ordinary baryonic matter. Every galaxy, every star, every planet, every atom in the observable universe accounts for less than 1/5 of the gravitational matter that cosmologists must include in their models to explain what they observe. What is dark matter? This is one of the 3 or 4 most important open questions in all of physics, and the honest answer is, we do not know. The candidates are numerous and diverse. Weakly interacting massive particles, or WIMPs, were for decades the most theoretically favored candidates. Particles with masses in the range of 10 to 1000 GeV, interactions with ordinary matter, mediated by the weak force, and a relic abundance from the early universe, naturally in the right range, to explain the observed dark matter density. This last property, that a WIMP with weak scale mass and interactions naturally produces a thermal relic density close to the observed dark matter density, was called the WIMP miracle, and it made WIMPs extraordinarily compelling theoretically. But direct detection experiments have now searched for WIMP interactions with ordinary matter across more than a decade, using detectors of increasing sensitivity buried deep underground to shield them from cosmic ray backgrounds. The LZ experiment, operating at the Sanford Underground Research Facility in South Dakota with a 10-ton liquid xenon target, and the X-Xenon experiment at the Gran Sasso Laboratory in Italy with a similar setup, have pushed the sensitivity to WIMP nucleon cross-sections down to levels well below what the original WIMP miracle prediction suggested. No confirmed detection. The simple WIMP has not appeared. This does not mean dark matter does not exist. The gravitational evidence is too strong, too consistent, too independently confirmed to doubt. But it suggests that if dark matter is a particle, it may be lighter than expected, and so harder to detect by current methods, or heavier, or interact more rarely with ordinary matter than the simplest WIMP models predict. Axions, extremely light particles, originally proposed to solve a different problem in particle physics, the strong CP problem, are an active alternative candidate. Primordial black holes formed in the early universe before any stars existed, have been constrained to be a subdominant component by a variety of observations, but have not been ruled out as a component of dark matter in certain mass ranges. Sterile neutrinos, hypothetical heavier cousins of the known neutrinos, are another class of candidate that connects to the baryon asymmetry problem through leptogenesis. What we do know is that whatever dark matter is, its properties were established in the early universe, in the era before the CMB wall. The relic density of dark matter, the amount that survived the hot early plasma to be present today, depends on the specific particle physics, the mass of the dark matter particle, its interaction cross-sections, and the temperature of the universe at which it decoupled from thermal equilibrium. All of these are properties of the era before 380,000 years. The CMB wall has locked away the direct observational evidence that would tell us what dark matter is. Dark energy is even more opaque, in every sense. The cosmological constant, the term in Einstein's field equations that represents a constant energy density of empty space, was reintroduced by Einstein himself, having earlier been abandoned, when observations in 1998 by Saul Perlmutter, Brian Schmidt, and Adam Rees, work that earned them the Nobel Prize in 2011, revealed that the expansion of the universe is accelerating. Distant Type Ia supernovae were dimmer than expected in a universe decelerating under its own gravity, implying that some form of energy was pushing the expansion to accelerate. Dark energy, whatever is responsible for this acceleration, constitutes approximately 68.3% of the universe's energy content, according to the Planck data. If it is the cosmological constant, its value must be extraordinarily small, about 120 orders of magnitude smaller than quantum field theory's naive estimate of the vacuum energy density. This discrepancy, between the theoretical expectation and the observed value, is arguably the worst fine-tuning problem in all of physics. Why is the cosmological constant so small? No one knows. Recent results from the Dark Energy Spectroscopic Instrument, DESI, have begun to suggest that dark energy may not be a pure cosmological constant. Its effective equation of state may be evolving slightly over cosmic time, hinting that dark energy is not just a fixed property of empty space, but a dynamic field, something more like a slowly evolving scalar field called quintessence. The statistical significance of this suggestion is currently around 3 to 4 sigma, suggestive but not conclusive. If confirmed by future data, it would imply that the nature of dark energy is not a cosmological constant, but something that changes over time, with a physics that traces back to conditions in the very early universe. Both dark matter and dark energy are, in their origins, phenomena of the early universe hidden behind the CMB wall. The properties that dark matter has today, its relic density, its spatial distribution, its influence on structure formation, were set in the first seconds or microseconds of cosmic history. The nature of dark energy, if it is dynamical, reflects processes that may have begun in the inflationary epoch or earlier. The wall does not just hide the Big Bang, it hides the explanation of most of the universe. Part 17. The Sound Horizon as a Cosmic Ruler, Measuring the Universe Across Time. There is a beautiful and somewhat underappreciated fact about the acoustic oscillations frozen in the CMB, which is that they have been leaving their mark not just once, at 380,000 years, but continuously throughout the subsequent history of the universe, and we can read those marks today in the distribution of galaxies. When the oscillations in the primordial plasma froze at recombination, the sound that had been propagating through the plasma also froze. The maximum distance that sound could have traveled through the plasma in 380,000 years, the sound horizon, is approximately 150 megaparsecs in today's universe, correcting for expansion. About 489 million light-years. This is a physical length scale that was imprinted on the distribution of matter at recombination and has been preserved in the statistics of galaxy clustering ever since. Galaxies are not distributed randomly in space. They cluster into filaments, sheets, and superclusters separated by vast voids. When statisticians analyze large catalogs of galaxy positions and look at how likely two galaxies are to be separated by various distances, they find a slight but statistically significant excess of galaxy pairs separated by roughly 489 million light-years, the baryon acoustic oscillation scale. This excess is the imprint of the sound horizon. The same acoustic oscillations that created the CMB temperature patterns also left a preferred separation scale in the matter distribution, and that scale is still visible today in the clustering statistics of billions of galaxies. The decay experiment, which is mapping the three-dimensional positions of tens of millions of galaxies out to distances of several billion light-years, is measuring the baryon acoustic oscillation scale at multiple cosmic epochs. Because the physical size of the sound horizon is known from CMB measurements, the apparent angular size of the baryon acoustic oscillation feature at different distances gives a direct measurement of how the expansion rate of the universe has changed over time. This is an extraordinarily powerful tool for measuring dark energy. What is remarkable about this is that a single physical scale, set by the physics of the primordial plasma before the CMB wall, has become a cosmic ruler that we use to measure the universe on the largest scales. The sound horizon is a calibrated standard. Its physical size is known from physics that was completed 380,000 years after the Big Bang, and its apparent size at different distances tells us the geometry and expansion history of the universe with exquisite precision. The baryon acoustic oscillation technique is in some ways the most direct connection between the era before the CMB wall and the observable universe today. The oscillations that froze at recombination are still visible in the universe we inhabit, embedded in the clustering of galaxies that formed over the subsequent 13.8 billion years. It is as if the wall left a signature on the universe, a set of marks that the subsequent evolution could not erase, that tells us exactly what conditions were like on the wall's other side. Every galaxy survey that maps the baryon acoustic oscillation scale is, in a sense, still listening to the sound of the primordial plasma. That sound stopped oscillating 13.8 billion years ago, when the universe went transparent, but its last note is still echoing in the distribution of matter, and we can hear it if we know where to listen. Part 18. The Hydrogen Window. What the First Stars Reveal. Between the CMB wall and the formation of the first stars, there is a period cosmologists call the Cosmic Dark Ages, from about 380,000 years to roughly 180 million years after the Big Bang. The universe contained no significant sources of light. Stars had not yet formed. There were no galaxies. The universe was filled with a nearly uniform gas of hydrogen and helium, slowly cooling and gradually developing the gravitational structures that would eventually collapse into the first stars. This era is called the Dark Ages, not because it was scientifically uninteresting. It was, in fact, deeply consequential, but because it produced no sources of electromagnetic radiation. The universe was dark, genuinely, completely dark. Observationally accessing the cosmic dark ages is one of the great challenges of the next generation of astronomy, and it relies on a very specific physical phenomenon, the 21-centimeter line of neutral hydrogen. This is the radio emission produced when a hydrogen atom's electron flips its spin relative to the proton, releasing a photon at a wavelength of 21 centimeters. It is the same hyperfine transition that radio astronomers use to map hydrogen gas throughout the Milky Way today. In the cosmic dark ages, the universe was filled with neutral hydrogen. Every one of those hydrogen atoms, in principle, was capable of emitting or absorbing 21-centimeter radiation. If we could observe the 21-centimeter emission from hydrogen at the redshifts corresponding to the dark ages, which, due to cosmic expansion, would be redshifted from 21 centimeters to frequencies of roughly 10 to 200 megahertz by the time it reached Earth, we would have a three-dimensional map of the hydrogen distribution in the universe from 380,000 years to the formation of the first stars. Such a map would be, quite literally, the most detailed observational picture of any cosmic era we could possibly obtain. The CMB gives us a two-dimensional snapshot of the universe at 380,000 years. Galaxy surveys give us three-dimensional maps of the universe from about 13 billion years ago to the present, but the galaxies are sparse tracers of the underlying matter distribution. The 21-centimeter signal from the dark ages would give us a three-dimensional map of neutral hydrogen density at every point in the universe, at every epoch of the dark ages and the subsequent reionization era, potentially with more information content than all other cosmological observations combined. The challenge is the radio frequency foregrounds. The Earth's ionosphere and the galaxy's own synchrotron radiation are millions of times brighter than the cosmological 21-centimeter signal. Separating the signal from this overwhelming noise requires either going to space, going to the far side of the moon, or extraordinarily precise spectrometric calibration of ground-based radio arrays. The hydrogen epoch of reionization array, the Murchison Wide Field Array in Western Australia, and other low-frequency radio telescopes are actively searching for the 21-centimeter signal from the epoch of reionization, the period when the first stars and galaxies ionized the surrounding neutral hydrogen. A tentative detection was reported in 2018 by the EDGES experiment in Australia, which found an anomalously deep absorption feature at a frequency corresponding to redshift 17, about 180 million years after the Big Bang, roughly when the first stars were forming. The depth of the absorption was greater than standard cosmological models predict, a possible indication of exotic physics such as interactions between dark matter and ordinary matter cooling the gas below the expected temperature. The EDGES detection remains controversial. Other experiments have not confirmed it, and systematic explanations have not been ruled out. Future experiments, including the Lunar Surface Electromagnetics experiment and proposed far side of Moon radio observatories, would escape the ionospheric interference that hampers Earth-based measurements. A radio telescope deployed on the Moon's far side, shielded from Earth's radio emissions by the bulk of the Moon itself, could potentially observe the 21-centimeter signal from the cosmic dark ages at frequencies unreachable from the ground. The first stars ended the dark ages, beginning the epoch of reionization. When the first stars formed, objects potentially hundreds of times more massive than the Sun, burning briefly and brilliantly before exploding as supernovae, their ultraviolet radiation began to ionize the surrounding hydrogen. This reionization process spread through the universe like a patchy fog being burned away, with ionized bubbles around early galaxies gradually growing and merging until, by about 1 billion years after the Big Bang, essentially all of the intergalactic hydrogen had been reionized. The universe had been dark and then became permanently transparent to ultraviolet light. The signature of this reionization epoch is visible in the spectra of very distant quasars, which show the absorption of their light by intervening neutral hydrogen, the so-called Gunn-Peterson trough, for quasars beyond a certain redshift. The James Webb Space Telescope, launched in December 2021 and operational since mid-2022, is specifically designed to observe galaxies in the epoch of reionization and the first stars, with infrared sensitivity optimized for detecting objects at the redshifts corresponding to the first few hundred million years of the universe's history. Webb has already revealed surprising results in its first years of observation, finding galaxies at redshifts above 10, corresponding to less than 500 million years after the Big Bang, that are more massive, more structured, and more evolved than standard models predicted. Some of these early massive galaxies have challenged the standard model of galaxy formation, suggesting either that stars and galaxies formed more efficiently in the early universe than expected, or that there is new physics in the early universe that accelerated structure formation. The community is actively debating whether the Webb observations require modifications to the cosmological model, or whether they can be accommodated within the existing framework, with adjustments to poorly constrained astrophysical processes. The epoch of reionization and the cosmic dark ages are not, strictly speaking, behind the CMB wall. They occur after 380,000 years, in principle accessible to electromagnetic observation, but they represent the furthest reach of current observational astronomy into the early universe, and they are the bridge between the plasma era hidden by the wall and the observable universe of galaxies and large-scale structure that we map today. Part 19. Time, Causality, and What Before Means, at the beginning. Every time someone asks what happened before the Big Bang, they are asking a question that has a genuinely subtle answer. Not because the answer is embarrassingly simple and we have not found it yet, but because the question itself may not be well formed in the way it appears. In general relativity, time is not a universal background against which events play out. Time is a dimension of space-time, a coordinate that is intrinsically bound up with the geometry and contents of the universe. The Big Bang, in standard general relativity extended to its singular point, is not just an event at the beginning of time, it is the beginning of space-time itself. Just as there is no south of the South Pole on the surface of a sphere, not because there is some barrier at the South Pole, but because the geometry simply does not extend in that direction, there may be no before the Big Bang, in the sense of earlier times that our universe emerged from. This is not merely a semantic point. It has physical content. In the Hartle-Hawking no-boundary proposal, the universe's wave function is computed using an integral over compact Euclidean four geometries in which imaginary time smoothly closes off at the beginning, the way latitude smoothly reaches a maximum value at the South Pole and does not continue into negative latitude. In this picture, the universe is self-contained. It does not emerge from a prior state. Its initial conditions are in some sense the most probable set compatible with the existence of a smooth, expanding universe. Whether this correctly describes reality depends on the validity of the semi-classical quantum gravity approximation used in the calculation, which is not guaranteed at Planck scale densities. But there are other frameworks. Loop quantum cosmology replaces the Big Bang singularity with a big bounce, a transition between a contracting phase and an expanding phase at Planck scale density. In this framework, our Big Bang is not the beginning of time, but a turning point. The universe existed before the bounce in a contracting phase, with a prior history that potentially extends arbitrarily far into the past. The quantum geometry effects that loop quantum gravity predicts at Planck densities prevent the singularity of classical general relativity from forming, allowing the universe to transition smoothly from contraction to expansion. If loop quantum cosmology is correct, then the question of what happened before the Big Bang has a meaningful answer. A contracting universe, with a prior history, with its own initial conditions set in the even earlier past. But this simply moves the question back. What determined the initial conditions of the contracting phase? Was there a beginning to that prior history, or is the universe eternal in both directions, bouncing forever with no first moment? These questions sit at the intersection of cosmology, quantum gravity, and philosophy of physics, and they are genuinely open. Not in the sense of being merely technically unsolved, the tools to answer them definitively may not yet exist. The wall at the very beginning of time is, in some ways, the hardest wall of all. Not because it is the farthest away, but because the very concepts we would use to describe what lies on the other side, time, causality, before and after, may not apply in the region we are trying to describe. The universe, as best we can tell from all available evidence, had a beginning in the sense of a state from which its current form evolved, a hot, dense, expanding state from which cosmic expansion and cooling proceeded to produce everything we observe. Whether that state had a prior cause, or whether it was in some sense self-causing, or whether the concept of causality applies at all to the question of the universe's origin, is a question that sits at the edge of what physics can currently address. Part 20. Every answer leads to a deeper wall. It is a recurring feature of fundamental physics that every question answered reveals a deeper question, and every wall crossed reveals a further wall beyond it. This is not a sign of failure. It is a sign that the universe has structure at every scale, that the explanations of what we observe always reach down to deeper foundations, and that those foundations have their own unexplained features. The CMB wall is not the last wall. Behind it, at 1 second, lies the neutrino decoupling wall, the moment before which even neutrinos were trapped in the plasma and cannot carry information to us directly. Behind that, at the quark-hadron transition, lies the hadronization wall, before which the particles that make up ordinary matter did not exist in their current form. Behind that, at the electroweak phase transition, lies the symmetry restoration wall, before which electromagnetism and the weak force were unified and the Higgs mechanism had not yet given mass to particles. Behind that, at the inflationary transition, lies the inflation wall, before which the universe may have been in a state so different from anything we can observe that standard cosmological extrapolations break down entirely. And behind all of that, at the Planck scale, lies the quantum gravity wall, beyond which our best theories simply fail. Each of these walls is a boundary of a different kind. The CMB wall is a wall of opacity. Photons could not travel freely before it. The neutrino wall is a wall of interaction rates. Neutrinos were coupled before it. The inflation wall is a wall of direct evidence. We can infer inflation from its aftermath but cannot directly observe it. The Planck wall is a wall of theoretical validity. General relativity and quantum field theory both break down there. What is extraordinary about the human scientific enterprise is that we have managed to reach, and in some cases partially pierce, walls that sit 13.8 billion years in the past. The first direct photons we can observe are 380,000 years old. The indirect neutrino signal is 1 second old. The inflationary gravitational wave signal, if it exists and we detect it, would be from 10 to the power of negative 32 seconds after the Big Bang. The Planck wall sits at 10 to the power of negative 43 seconds, and though we cannot observe what lies on its other side, we have identified precisely where it is, what physics breaks down there, and what kind of theory we would need to pass through it. This progression, from the CMB wall at 380,000 years back toward the Planck wall at 10 to the power of negative 43 seconds, covers 49 orders of magnitude in time, 49 powers of 10 in the age of the universe, and in that entire span, the universe's history is not empty or featureless. Each epoch has its own distinctive physics, its own processes, its own contribution to the conditions we observe today. The matter in your body was cooked in the first 3 minutes. The conditions that allowed that cooking were set in the first microsecond. The seeds of the galaxy that contains your sun were quantum fluctuations from the first 10 to the power of negative 32 seconds. And the initial conditions that determined all of it were set in the first moment, at the Planck scale, in an epoch we cannot yet describe. The universe has multiple walls, at multiple depths in its past. We are standing in front of the first one, the CMB wall at 380,000 years, and we can already see the outlines of the deeper walls behind it. The project of cosmology is to build, one by one, the tools that let us pierce each wall in turn, moving backward in time with each advance, until we either reach the beginning or discover that the beginning is not what we thought it was. And if the history of physics is any guide, what we find on the other side of each wall will be stranger, more surprising, and more beautiful than what we imagined before we crossed it. The universe does not reward complacency, but it rewards patience, precision, and the willingness to ask the next question, and the next one, and the next one, no matter how many walls lie between us and the answer. If this video added something to your understanding of the cosmos, or if it made the questions feel larger than they did before, leave a like. It matters more than you might think for getting this content in front of people who would appreciate it. And subscribe, because there is so much more of this to explore. We are small creatures in an enormous universe, sitting in front of an ancient wall of light, slowly building the tools to see through it, and that might be the most remarkable thing there is. End of script. Appendix. The universe as a question, a final meditation on the wall. It is worth sitting with something before we close this. The cosmic microwave background, that faint, cold, 2.725 Kelvin glow that fills the sky in every direction simultaneously, is not something most people have ever thought about as a physical object with a location. It sounds abstract, like a theoretical construct, but it is not. Right now, as you listen to or read these words, the CMB photons are passing through you, billions of them every second. They have been traveling since before the Earth existed, since before the Sun ignited, since before the first galaxy organized itself from primordial gas. They have crossed distances that make the distance from Earth to the nearest star seem like a step across a room, and they are passing through your body without interacting with it at all, just as they have been passing through everything in the universe for the last 13.8 billion years. The wall is not far away and abstract. It is everywhere, all at once, and it is constantly streaming through you. There is a certain quality to that fact that is difficult to articulate without sounding hyperbolic, but which is, actually, just accurate. The oldest light in existence is passing through your body right now. It was released when the universe was 380,000 years old, when there were no stars, no galaxies, no planets, no atoms heavier than lithium, no chemistry, no biology, no anything that we would recognize as organized complexity. It has been traveling since then, and right now, at this moment, it is here. The wall that physicists cannot see past is not a wall at the end of a journey. It is a wall that is right here, in this room, in this moment, in the body that is doing the reading or listening. The surface of last scattering is a sphere around you, 46.5 billion light-years in radius, centered precisely on where you are sitting. Every direction you look is the wall is the sky. When Arno Penzias and Robert Wilson first detected the CMB in 1964, they did not know what they had found. They were using a large radio antenna designed for satellite communications at Bell Laboratories in New Jersey, and they kept finding an excess noise signal they could not explain or eliminate. They tried everything. They pointed the antenna at the sky in different directions. They checked the electronics. They found that pigeons had been roosting inside the horn antenna and had coated it with a layer of droppings. They cleaned it. The signal persisted. No matter where they pointed the antenna, no matter what they tried, the noise was there, equally, from every direction. What they had stumbled into was the oldest light in the universe, filling the sky uniformly from all sides, arriving from 13.8 billion years of cosmic history, and completely indifferent to their attempts to get rid of it. The CMB is not going anywhere. It will be here, pervading the cosmos, for a very long time. As the universe continues to expand, the photons will continue to redshift, their wavelengths stretching longer, and their temperatures dropping lower. In 1 trillion years, the CMB temperature will be so low, and the photons so redshifted, that no instrument we can currently imagine would be able to detect them against the background of quantum noise. The wall will not disappear, but it will become, in the far future, even harder to read. Which means now, in this era, in this epoch of cosmic history, is actually an extraordinarily privileged moment in which to exist and ask questions about the wall. The CMB is detectable now. The baryon acoustic oscillations are visible in the galaxy distribution now. The technology to search for primordial gravitational waves is being built now. The neutrino background will become more accessible as detector technology advances over the coming decades. We live in the era of cosmic archaeology. The tools are just becoming sharp enough, the questions just becoming clear enough, and the data just becoming rich enough that we are beginning to extract the history of the early universe from the ancient signals it left behind. Future generations, perhaps centuries from now, perhaps millennia, will look back at this period the way we look back at the first optical telescopes of the 17th century, not as the era when we had the answers, but as the era when we realized what the questions were and began to develop the instruments that would make them answerable. The wall stands. It has always stood. Everything in the universe on this side of it, every atom, every star, every galaxy, every observer who has ever looked at the night sky and wondered, emerged from what lies beyond it. The universe's birth certificate is written on the wall, in the language of acoustic oscillations and temperature fluctuations and polarization patterns. We are learning to read it. We have not finished. We may never finish. But the reading itself, the slow, careful, precise, collaborative enterprise of extracting meaning from ancient light, is itself one of the most remarkable things that has happened in the 13.8 billion years since the wall was formed. The universe made something that can wonder about the universe, and that something is now standing at the oldest light in existence, asking what it hides. There is no more fundamental question than the one that wall silently poses, and there is no more human response than the one we have been giving it. We are building better instruments. We will look again. We will not stop looking. The wall is there. We are here, and the distance between us and what lies beyond it is, slowly, getting smaller. End of script. Total runtime estimate. Approximately 2 hours 20 minutes at standard narration pace. A note on the science. Sources and accuracy. Everything in this script is grounded in established or actively researched science. The CMB temperature of 2.725 Kelvin, the recombination epoch at approximately 380,000 years after the Big Bang, the composition percentages from Planck 2018 data, the baryon acoustic oscillation scale at roughly 489 million light-years, the baryon asymmetry parameter of approximately 6 × 10 to the negative 10, the Ptolemy experiment's projected detection rate of roughly 9.5 neutrino capture events per year with 100 grams of tritium, the quark-gluon plasma existing in the first microsecond, Big Bang nucleosynthesis completing within the first 20 minutes, and the formation of the first stars at roughly 180 million years. All of these are current scientific consensus values. The inflationary model remains the leading theoretical framework, but has not been confirmed by direct observation. The detection of a stochastic gravitational wave background by Nanograv and partner collaborations in 2023 is real and confirmed, though its interpretation as astrophysical versus cosmological in origin is actively debated. The DESI hints of evolving dark energy are at a 3 to 4 sigma level as of 2025 and 2026 and remain under investigation. The edges anomaly in the 21 centimeter signal is unconfirmed and contested. Dark matter and dark energy exist as observational facts. Their gravitational effects are measured and consistent across multiple independent techniques. Their physical nature remains unknown. These are honest representations of where the science stands. The soul of this script is not to present a solved picture. It is to present the actual state of knowledge, with its genuine uncertainties and genuine achievements, and to convey why the questions that remain open are worth the extraordinary effort being devoted to answering them. The universe is strange, the wall is real, and we are just beginning to learn what it is hiding. The CMB wall stands at the edge of everything we can directly observe. It is made of the oldest photons in existence. It was formed when the universe was 380,000 years old, when protons and electrons combined into neutral hydrogen for the first time, when the plasma that filled all of space finally cleared and became transparent to light. The photons released in that moment have been traveling ever since. They are old beyond the capacity of normal language to express. They are here now. They are always here, and they carry, encoded in their temperature and their polarization, and the subtle statistical patterns of their distribution across the sky, more information about the early universe than any other signal we have ever detected or are likely to detect through any electromagnetic means. Behind the wall, in the 380,000 years between the Big Bang and recombination, the universe lived a first life that we can reconstruct only in outline. The plasma era, the quark-gluon plasma, the formation of the first protons, the neutrons that decayed, and the ones that were incorporated into helium nuclei before they had the chance. The acoustic oscillations that rang through the plasma, like the harmonics of a vast, hot, pressurized sphere, the baryogenesis events that broke the symmetry between matter and antimatter, and produced, from the near-perfect cancellation of those two opposing quantities, the 1 in 10 billion excess that became every atom that has ever existed, the inflation that stretched quantum fluctuations from subatomic scales to the scales of galaxy clusters, and before all of that, the Planck epoch, the first 10 to the power of -43 seconds, the realm of quantum gravity, where our understanding ends and the deepest questions begin. This is what the wall hides. This is what we are trying to read, one careful measurement at a time, in the faint signals left behind by an era that ended before the first star had formed, before the first galaxy had coalesced, before the first atom of carbon had been forged in any stellar furnace. The universe was 13.8 billion years old when we started asking these questions in any systematic way, and it has been 13.8 billion years in the making. We are late arrivals, looking back at a history that was complete before we existed, trying to read a record that was written before there was anyone to write it. The universe keeps its secrets in light, and light, for once, is what the wall will not let through its